Welcome to today's explainer. Imagine if you could just crack open a futuristic digital notebook and literally decode the universe's source code. Well, that is exactly what we're going to do today. We're going to act as cosmic detectives, starting with something as unimaginably massive as planetary orbits, and we're going to decode the underlying rules that govern them. And the best part? By the end of this explainer, we're going to bring those exact same cosmic rules right back down to Earth to explain a really fascinating, everyday mystery that's probably happening right on your desk.
Here's our roadmap for today. 1. Forces of circular motion. 2. Defining center of mass. 3. Newton's mathematical masterpiece. And 4. The everyday gravity mystery. Let's dive in.
Section 1. Forces of circular motion. The rules of the simulation.
So, to really understand the cosmos, we first have to figure out the basic rules of our cosmic simulation. Think about a planet orbiting the sun. What keeps it moving in that perfect circle instead of just, flying off into the void of space? The answer is centripetal force. By definition, when an object moves along a circular path with a uniform or constant speed, its motion is sustained by a continuous center-seeking force. You can kind of think of it as an invisible tether. Because without this constant pull toward the center, uniform circular motion simply cannot exist. The object would literally just travel in a straight line forever.
Now, what's absolutely fascinating about this concept is how elegantly it's expressed mathematically. This right here is the structural formula for centripetal force. F is the magnitude of the force, and that's equal to m, which is the mass of our moving object, multiplied by v squared, its linear orbital speed, and then all of that is divided by r, the radius of its circular path. This single elegant equation is essentially the engine driving our entire cosmic simulation today.
Section 2. Defining center of mass, pinpointing the core.
Okay, so to use that centripetal force formula accurately, we need to know exactly how to geometrically define the mass of these massive orbiting bodies. Planets are huge, bulky spheres, right? So where exactly do we measure that radius from? Well, we do this using the center of mass. This is defined as the unique point, which surprisingly can actually be inside or outside the body, where its entire aggregate mass can be assumed to be concentrated. To make the orbital math work flawlessly, we don't calculate the pull on every single atom of a planet. That would be impossible. Instead, we assume all of that object's aggregate mass sits perfectly at one single unique point.
So, the trick is knowing exactly where that unique point is rendered in our universe. For a perfectly spherical object with completely uniform density, which is how we usually model planets, the center of mass lies precisely at its geometrical center. Easy enough. But for a non-spherical object, like a perfectly symmetrical box, that aggregate mass is located directly at its geometric centroid. This specific anchor point is absolutely crucial because it allows all the orbital math that follows to function perfectly.
Section 3. Newton's mathematical masterpiece. Cracking the case.
All right, now we're ready to step into the shoes of the ultimate cosmic detective, Isaac Newton. He took these foundational rules of circular motion and mass that we just talked about, and he used them to connect orbits directly to gravity. His ultimate goal? To mathematically prove that the gravitational force between the sun and a planet is inversely proportional to the square of the distance separating them. That's what F is proportional to 1 over r squared actually means. And his master key to solving this whole thing was Kepler's third law of planetary motion, which states that the period of revolution squared divided by the orbital radius cubed equals a constant, represented by the letter k.
Newton cracked this code in 4 methodical algebraic steps. First, he expressed orbital speed. Next, he substituted that into our centripetal force formula. Then, he cleverly injected Kepler's law. And finally, he made his brilliant mathematical inference. I really want you to follow this beautiful piece of logic closely with me, because it literally changes everything.
First up, step 1. Let's assume a planet moves around the sun in a uniform circular orbit of radius r. How fast is it going? Well, linear speed, or v, is simply the distance traveled divided by the time it took. The distance is just the perimeter of the orbit, which is 2 pi r, and the time taken for one full revolution is the period, which we denote with a capital T. So, velocity v equals 2 pi r divided by t.
Next up, step 2. We take that value we just found for v and we plug it directly back into our structural centripetal force equation. So force, F, equals mv squared over r times the quantity of 2 pi r over t squared. When you actually square that fraction, you get 4 pi squared r squared over t squared. Now we simplify the radius variable by canceling out one of the r's, and we're left with this. F equals 4m pi squared r, all divided by t squared.
Okay, step 3. This is where Newton's absolute genius shines. He needed to get Kepler's constant, which, remember, involves r cubed over t squared, into this equation. So what did he do? He altered the fraction. He multiplied both the numerator and the denominator by r squared. This gives us r cubed on top. By rearranging the terms, we isolate the inverse components of Kepler's constant. Since t squared over r cubed equals k, that means r cubed over t squared equals 1 over k. Substituting that in leaves us with this final equation. F equals 4m pi squared divided by r squared times k.
Now, take a really close look at that fraction. Newton realized something profound here. The mass of the planet, m, well, that's a constant. Pi is, of course, a constant. And Kepler's value, k, is a completely invariant constant for a specific orbit. Because all of these are constants, that entire cluster of terms, 4m pi squared over k, functions entirely as just one single constant value.
Which brings us to step 4, the grand conclusion. If everything else in the top of the equation is a constant, then the force F changes only based on the radius. Therefore, F is inversely proportional to the square of the distance, or 1 over r squared. Newton triumphantly concluded that the fundamental centripetal force holding planets in orbit maps perfectly and directly to the universal force of gravity. He proved it. The math works out flawlessly.
Section 4. The everyday gravity mystery, bringing it back down to Earth.
So, we've solved the cosmic code, but let's bring it back down to Earth. Because honestly, the most amazing part of Newton's discovery is that these exact same rules apply right in front of you every single day. I want you to use your brain power for a second and apply Newton's rule to your immediate surroundings right now. Think about two objects sitting on a table, or maybe think about yourself and a friend sitting next to you. Is there a gravitational force between you two right now?
Believe it or not, the answer is a resounding yes. A mutual gravitational force of attraction absolutely exists between you and your friend and between your phone and your coffee cup. Newton's law dictates that every mass attracts every other mass universally. There are absolutely no exceptions in the cosmic simulation.
So, why aren't you and your friends suddenly flying across the room toward each other? Well, it all comes down to this exceptionally minuscule number right here, the universal gravitational constant, or big G. The value of G is 6.673 times 10 to the power of negative 11 newtons meter squared per kilogram squared. Guys, that is a decimal point, 10 zeros, and then a 6. Because this number is so incredibly tiny, the net gravitational pull generated between ordinary, small, everyday masses, like humans or books, evaluates to a microscopic fraction of a newton.
That tiny attractive force is definitely there, for sure. But when we compare that microscopic gravitational pull against the environment, it completely loses the battle. It is totally countered and overcome by the much larger opposing forces of static friction. The friction acting between your feet and the floor, or between your everyday objects and the table surface, is vastly stronger than the gravitational pull between them. To truly see gravity take the steering wheel, a planetary scale is required. Gravitational forces only become dominant, capable of actually controlling structural movement and overriding other forces like friction, when at least one of the interacting bodies possesses a massive planetary scale of mass. We're talking about the Earth, the Moon, or the stars. But here's the crazy part. Even though friction keeps you sitting perfectly still in your chair right now, Newton's math proves that you are literally tethered to everything around you by this invisible cosmic code. You are pulling on the universe right now with your own gravitational force, and the massive universe is pulling right back. So the next time you look at a coffee cup resting quietly on your desk, ask yourself, what other invisible forces are holding your world together? Keep exploring, keep questioning, and I really hope this explainer helped you decode just a little bit more of our incredible universe.